Witness the incredible process of crafting a colossal gear-bearing ring. It was only at the end that we realized why a seemingly simple aircraft carrier component can weigh up to 800 kilograms? A single combined bearing assembly requires hundreds of meticulous steps. To meet the extreme specifications of this metal giant, precision must be maintained within an astonishing 0.1 micron. The craftsmanship here truly defies imagination. We're inside a renowned local gear manufacturing plant. The first step in forging this massive bearing. Step 1. Workers use forklifts to place raw materials onto the cutting platform. Once positioned accurately on the prep station, the automated blade descends and slices through with precision. It takes just 25 minutes in total, and the blank for the inner gear shaft is ready. As a key part of the carrier system, this raw material is no ordinary steel. Take a close look at the cross-section. This steel composition is vastly different from regular industrial steel. Its primary purpose? To dramatically enhance wear resistance. The forklift then stacks 5 slabs together and loads them into an electric furnace, ready for intense heating at a scorching 1,200 degrees Celsius. To conserve energy, the furnace is packed to capacity during every batch, but this also means longer heating times are required. The furnace is sealed shut to accelerate the heat-up phase. Meanwhile, temperature is constantly monitored through sensors. The figure you see here is the internal furnace temperature. When the furnace door finally opens, it signals the end of this high-temperature phase. But there's no time to rest. Steel blocks must be quickly transferred using mechanical arms and delivered down below, where molten metal awaits. It may seem minor now, but it precedes a massive transformation. Only a small amount is actually used. The brittle oxidized layer on the surface crumbles away completely. Then the piece is rotated and the angled edges are flattened until both sides begin to show surface distortion. Eventually, the final deformation position is locked in place. Looking at the footage, the metal deformation happens at incredible speed. Only 4 to 5 compressions are needed to shape it into a large circular disc. It's then pressed rhythmically to distribute pressure evenly across the steel. This continues until the final prep is completed. Next, the piece moves forward to meet a massive mold that's been waiting. As shown here, this mold is carved from a solid steel cylinder. Once in position, workers clamp the piece securely in the center of the cylinder. Then a top ram applies powerful hydraulic pressure from above, continuously forcing it downward, while simultaneously grinding the edges until the steel is completely pierced through. As we can see here, under extreme pressure, the solid steel's internal structure begins to shift and compress. This marks the start of the second phase. The operator uses a lift to place 2 of the steel discs into the furnace. They're reheated alongside the remaining 2 pieces. Compared to earlier, this round of heating takes far less time to reach optimal temperature. But in terms of process intensity, what comes next is the most critical and dramatic step of all. It's called ring pressing, or suspended pressure forming. Before it begins, the steel is transported to a powerful ring-forming press. Then a robust fixture locks the piece in place for precision shaping. Just like you see right here, once the PT is secured in place, 3 additional groups are moved in simultaneously. Each of the next 3 roller sets contains 47 rollers. As the pressing begins, the core is gradually extruded outward. The iron ring expands bit by bit under synchronized pressure. During this process, a large volume of clean water is sprayed to cool the rollers continuously. At this point, a neatly edged iron ring has taken shape. Although it may appear straightforward, in reality, it often takes over 30 minutes to complete this step, especially when it comes to angle and precision. Even the slightest error is unacceptable. So, a worker carries a measuring plate to inspect the ring. The top of the plate is marked with extremely fine scales, using both the step marks and diagonal lines on the plate. The worker carefully measures the full circumference of the ring. Only once the inner diameter matches the specified dimensions, The piece is removed and taken outdoors for extended natural cooling. Once cooling is complete, the ring is then placed on a platform and carefully stacked in a designated staging area. This becomes the most time-consuming stage in the entire fabrication cycle. Each batch must be reheated in the furnace for up to 15 hours. Yes, you heard that right. A full 15 hours of continuous heating. That's why heat treatment usually continues past working hours. By the time the heated stage finishes in the furnace, it's already the next morning. Workers then open the furnace door, and the processed ring returns to normal temperature. Only now is it ready to meet the strict pre-cutting standards. Then it's lifted and moved to the next workshop. Here, the outer layer of the collar ring will be precisely trimmed. That's why accuracy requirements at this stage are extremely high. The worker begins with a single alignment. A micrometer plate, damaged and intact, is mounted on the machine base at a fixed angle. It's then moved vertically to align with the steel ring's edge. The measuring tool is activated and steel measurements begin. The purpose of this step? To determine the precise cutting position. Even the slightest deviation requires the worker to bring out a wrench. They rotate the steel ring carefully into place. This inspection process usually takes at least 10 minutes per piece. And after adjustment, it isn't cut right away. Instead, the ring is rotated back to recheck the alignment point, only when all positions are confirmed. Do workers begin tightening the bolts one by one? At this stage, pre-cutting procedures are basically complete. Next, the lathe machine is activated to trim the outer ring. During machining, large volumes of cutting fluid are sprayed. This helps keep the cutting blade cool throughout the process. The goal, a clean, neat-edged, semi-finished product. At this point, the inner frame of the massive bearing has taken its final form. Now, let's examine the finer details. In terms of precision, it meets the exacting standard of 0.1 microns. Next comes the quality test. The steel ring must be flawless. No excess cuts, no missed edges throughout the process. Any undercutting issues would also mean a loss of precious time. And did you know? Just moments ago, this machine performed a powerful 2-hour cut. Now it moves on to the next step, gear tooth fabrication. The equipment you see here is designed to produce the gear surface teeth. Before beginning, workers must first disassemble the previous cutting tool. A different type of cutting blade is randomly swapped in. Each blade has a unique profile, so the corresponding spacing must also be adjusted. Then bolts on both sides are tightened firmly. Next, the worker moves to the other side to start the equipment. You'll soon see the transmission activate. The high-speed cutting head kicks in. And in terms of cutting efficiency, it's impressively fast, especially on the visible tooth surfaces, which are formed almost like the outer ring process, providing solid structural drive. As for the cutting method, it begins with precise, evenly spaced cuts. Then each groove is carved one by one based on spacing. At this point, the overall gear shape is already formed, and that densely packed tooth pattern might seem instantaneous in the video, but in real-world machining, it takes a total of 76 detailed steps to complete. Only then is the formation finished. Next, the part is removed and inspected for surface quality. Even the measuring tools are specialized here. At the moment, only a large caliper is being used to meet the current measuring demands. Once the inspection is complete, this gear ring is officially done. Now both the inner and outer gear components are ready, and the final step of the process begins. First, the inner bearing component is placed onto oil drums. Then the outer ring is carefully lifted above. and slowly lowered to align with the inner component. At this point, the two parts can be precisely joined together with perfect alignment. Another crucial element is now ready to be inserted: the ball bearings. Balls are common in bearings, of course, but ones larger than a fingernail are extremely rare, especially when paired with white separators, which guide the placement. The installation process at this stage is also quite unique. Each ball must be precisely aligned with its separator slot. The white separator's main function is to maintain spacing. It helps reduce friction between the balls during operation. Once the final ball is placed, the worker manually rotates the assembly to inspect it. Are there any defects? Visual checks can often spot missing balls. If any are missing, a visible gap will remain in that position. If there's a gap, the ball must be removed and reinserted immediately. In the blink of an eye, the final balls are secured into place. Then the long-prepared retainer block is inserted. That's the piece of solid metal we see here. Finally, a locking rod is inserted into the assembly. This ensures that the structure is held together and won't fall apart. The entire ring is then rotated slowly to check smooth movement. Next, golden-colored lubricant is added to the ball gear system. The grease reduces the coefficient of friction and significantly enhances the bearings' stability during operation. This process requires simultaneous rotation and injection. That way, the grease fills every tiny gap completely. Next comes the step of sealing the outer layer. The material used is a rubber strip as shown here. First, the worker applies sealing adhesive. Every gap is completely filled. Then the pre-cut rubber strip is laid on top and firmly pressed in place. To secure the first layer, a shock guiding rod is used to press the tape fully into position. The primary function of this sealing strip is insulation, protecting the unit from moisture and dirt. Next, scissors are used to trim the ends of the final strip. Then adhesive is reapplied along the brake line for a strong bond. Both sides are pressed tightly together for a clean finish. To meet high-quality standards, even this final seam must be flawlessly sealed. At this stage, a giant gear bearing has been fully assembled. But before it leaves the factory, it must undergo manual inspection, which can be physically demanding. Because after all the grease is applied, ball resistance is significantly reduced. So how much do you think this big guy weighs? A solid 800 kilograms. That's 1,600 pounds. It might not look like it, but this thing is incredibly heavy. So when it comes to a massive bearing like this, what do you think?